Hello and welcome to the presentation on achieving timing awareness for the dynamic runtime architecture of ECU projects within CI environments. My name is Florian Sommer. I'm responsible for the business development for the product line embedded software here at Vector Informatik in Stuttgart, and I'm going to guide you through this presentation today. So, first of all, let's get a first overview on timing awareness and on the agenda that we are going to cover today. First of all, I think I'm not telling you anything new if I say the complexity of ECU projects is constantly increasing, and the reason for that is on the one hand the software itself. So software is getting more and more complex. Software is also is more and more also differentiator for the end consumer in the car, and more innovations in the automotive industry are driven by software. So no wonder we get more software that somehow needs to be integrated and makes in the end the hardware also more complex to be used. So we are not only talking about single core microcontrollers anymore, but we are using multiple cores within the microcontroller, and it also quite common to use microprocessors meanwhile. With the same, we also get a mix of AUTOSAR Classic and AUTOSAR Adaptive. Need to handle that complexity as well. And additionally to that, we also have somehow a change in the way the collaboration works within the automotive industry. When in the past you had single ECUs providing single functionalities, and they were provided by one tier one, this changed in the past. So meanwhile, it's quite common that there's one software supplier responsible for the integration of the software, but maybe he doesn't develop all the software components on his own. So there might be software components that come from third parties. There might be software components that you develop on your own, but also maybe some software components that are provided by the OEM himself and need to be integrated. And all these software parts somehow need to work together. And I guess continuous integration and doing nightly builds, or at least weekly, is something quite commonly used. But one topic that comes in here as well is the topic timing awareness. So how can timing awareness help to handle this complexity? When we're talking about timing awareness, I think one very common thing that is very often looked at is the CPU load. So how does the load in the system develop over the course of the development? So you could measure, for example, the time that the system spends in the idle task with each build that you do, for example, and this would allow you to get a very nice graphics so you can monitor how the different releases influence the load in your system. But there are also other topics that you can check on different levels, which we will cover later. So how can the awareness of the timing within your ECU system help you to handle this complexity? I see a couple of open questions on this topic that I want to cover in today's presentation. So one is, what is timing awareness on a more detailed level? So how can I analyze the timing? What different metrics are considered and how do we measure it at all? Then we will see a very practical example that should show you how this timing awareness can really help you to improve a system. And we will learn which tools are needed and also what are the necessary steps in the different tools to get to timing awareness. And in the end, of course, also how can this be automated so that you don't need to do the steps manually all the time. So let's jump right in to the topic, what is timing awareness? You have seen this very small on the previous slide already. We have different timing aspects in different phases of a project, and we have different perspectives on timing. So the first one is here on a software architecture design level. You of course know on an architectural level which functionalities different software components need to fulfill. So in this example, we have one software component that is reading sensor data. Then we have an application software component which is then processing these data in two different runnables. And we have a third actuator software component which in the end is making a decision for an actuator based on the processed data. What you can see here drawn in green is called the event chain. So if you have such a behavior, if you have modeled it in your architecture design, you want to make sure that this event chain is executed in the right order afterwards when you run it on your microcontroller. And you might also want to ensure that from reading the sensor data until making a decision for the actuator, it doesn't take more than 100 milliseconds, for example. So these are things that you can derive from your software architecture and that you can later check once you have integrated it. Then as a next step, we would now need to break down the runnables and integrate them into our basic software. So somehow we will need to map all these different runnables to different tasks, which might get triggered by an ISR or which are triggered periodically, like the 10 or 5 millisecond periodic task that we see here. And all of them, depending on how they are triggered or depending on if they're preemptive or not, and on their priority, will be executed within the system that we have defined later on when we're about to realize the functionality. And timing awareness now allows you to check all these different parameters, the event chain, the activation of your tasks, the overall load in the system, the balancing between the different cores. All these metrics can be measured and can be tested in an automated way so that you're always aware of how much runtime is which task consuming, how much load do we have in overall in the system, and also is the kind of activations that we have, are they correct? So are the 5 millisecond tasks really activated every 5 milliseconds or not? Let's have a look at the scheduling activities itself. I want to give you a little bit a better feeling what exactly are we looking at when we're talking about this kind of timing awareness and the different metrics. So first of all, we will need to learn a little bit more about the state changes of the tasks and the scheduling trace that can be recorded with the toolchain I will show you later. Here on the right side, you can see the different state transitions that a task can have within the Microsoft OS. And what we will do later on is basically to create a log file, a scheduling trace, which provides you always the information in a CSV format at which timestamp, which entity, so which task performed which state transition. So if we would walk through this model, what we would see now with our example task at the timestamp 1 millisecond, this task gets activated. So this means it's active, but it's not running on the core because another task with higher priority is still active. Now, after 1 millisecond, this task turns into the running mode. So it's now actively running on the core. From there, it has two possibilities. It could be preempted or it could be terminated. Now here we are getting preempted because there's another task with a higher priority, which is now running on this core. Then at the end of this period, the task gets back to running and now finally gets terminated and suspended. And with this timeline, you can now already find out a lot about the timing behavior of this task. And now this is only one task, but if you imagine you can do this for your whole tasks and all your runtables in your system, then you can really get out a lot of information from that. And we will see in a second why. But before we jump to the example, let me mention a couple of basic metrics that can help you to analyze such a scheduling trace result. First is the response time. The response time is the time between the activation and the termination of one task. So it covers the whole time. So every aspect of the task is considered. So when it's actively waiting to run on the core, when it's running, when it's preempted, running again, preempted, and so on. The next net execution time, however, this metric only counts the time where your task is really actively running on the core. So shown in this dark green color and indicated by these red arrows here. And the net execution time is simply summarizing all these active running states of a task and then provides you the net execution time. Additionally to that, we have here the start delay, which is the time between the activation and the first time the task starts to actively run on the core. And if we now combine these three metrics, we can already learn only from looking at a static metric, we can already learn a lot about the behavior of this task. For example, if we have 1 millisecond periodic task and its response time is at 1.2 milliseconds. This would give us an indication that there's definitely something wrong, because the periodic task would be activated again after 1 millisecond, but it only finishes after 1.2. So there's definitely a problem with that. If we dive in a little deeper, we can then in the next step analyze, okay, why is the response time so long? Is this task really taking 1.2 milliseconds in a running state, or does it maybe have a very long start delay and doesn't get to run until the very end and is then finished very soon, or is it preempted a lot of times? The next thing we have is the activate to activate time. Activate to activate, quite simple, the time between two consecutive activations, and the start to start time is the time between the first and the next really start or the active running of the task on the core. And if we have a look at this also gives us a very good indication to understand, for example, for periodic tasks, are my periodic tasks really activated within the period, or is maybe my 10 millisecond task activated every 1.5 milliseconds, for example? That would be a problem. Okay, so much about the basic metrics. One hint for all the metrics that I show you here, and for many others as well, you can directly create requirements that will later be checked against the scheduling trace in the project again and again. So if you say, for example, for all my periodic tasks, I want to make sure that the activation of these periodic tasks is within plus minus 10% of its period, that's something you can automatically derive and check as a requirement every time. So much about this. So we've learned, it looks like it makes sense that we have some kind of timing awareness. So why is there such a lack of timing awareness? There are basically three big reasons for that that we face again and again. One is, in the mindset of many people, analyzing the timing is something you do only in error cases. So if we have 100% CPU load, then we would do a timing analysis. Then we would look into the detail. You will see later why it's helpful to have it all the time. The next thing is, many people see setting up a timing toolchain as very time consuming, and that a lot of manual configuration and different manual steps are necessary. And the third reason why there's such a lack of timing awareness in projects is that timing analysis is considered as a very complex topic, and also the setup and the tools that need to be combined and work together are very complex and make it huge manual effort to use it. Today, within this presentation, I'm here to prove to you that this is not the case, that it's possible to do this in a simple way, not only while debugging, but also continuously throughout the whole project. And our solution from Vector to do that is the Timing Architects tool suite. Let's move to the next chapter. How can timing awareness help to improve the system? In this chapter, I first of all want to give you a practical example that we were able to solve. And then we are going to think about how can we check this finding in an automated way throughout the next steps of the project. So what do we see here? We are having here a project which has an overall CPU load of around about 56%. So it doesn't look like we would need a timing analysis here because the load is not 100% yet. Additionally to that, we have here a timeline. So we see here on the x-axis the milliseconds, and we see here the CPU utilization in percentage. And what we can learn from that is that we sometimes have some bursts or spikes in the load in the system. So as a next step, we want to investigate in a little bit more detail this time frame here where we had the spikes, and have a look at the Gantt chart, where we see now the actual timing behavior of the overall system. What we see here in the Gantt chart again is down there, x-axis is the time, and we can see here the different cores, and that on the cores there are different tasks and runnables running on these. The tasks are indicated here with these the colors here, green colors. So you can see preemptions, you can see them actively running, and below there, if the color is blue, then we have the actual runnables that run inside these tasks. So within this task and within this task, we have runnables that are displayed here right now. And so what can we learn from looking at this this Gantt chart? Maybe one thing that's interesting to know is what kind of issue are we looking at. So we learned the overall load is with 56% is not very high, so it should be okay. But the problem that we had in this case was that sporadically the communication was broken, so there was no communication happening over CAN anymore. That was the issue. So we now tried to find out what's the reason for that. So why isn't there any communication ongoing at a certain point in time? And what's interesting, if you look on a timeline perspective at this topic now, is that within these 5.53 milliseconds where we have the increase in the load, what we can see is that there are several things happening in parallel. The one is up here, we see that there's a very high ISR load that is happening. Additionally to that, you can find here within this task one runnable which is consuming a lot of runtime. So it takes around about 5.53 milliseconds from activation to termination. So the response time is very long. And now here comes the necessity to understand the system in more detail. The question is, what is this runnable actually doing? And what this runnable was responsible for was the communication between two cores. And this communication took more than 5 milliseconds, which is quite long. And the combination of these two effects, high ISR load and the this cross-core communication runnable was activated, led to the fact that below here we can see that CAN messages get dropped. So before that, we have here quite regularly the CAN-TP running, but here during this time frame, we are missing messages, and this leads to a breakdown of the communication. I think this is a very good example that allows us to see why timing awareness is something that's not only helpful in debugging or overloaded situations, but also in systems where you don't think that you have too much load. It can still happen that there are some scheduling activities interfering with each other, which actually cause real problems that you would very, very hardly find. So this combination that the drop of the CAN message is here caused by these two effects is something that is very unlikely to find out without such a level of detail. So let's consider we found the issue, and now in the next step, for the future builds of our software, we want to have a requirement which ensures that this doesn't happen again. So what can we do? We can see here below that this CAN-TP main function is executed or activated quite periodically. And if you look in detail, the average activate to activate time is around about 2 milliseconds. So the taking the activation, the periodic activation of this runnable as a requirement might be a good idea, because if we are missing out such a huge gap like here with more than 5 milliseconds, then obviously we have a problem. So we could try to define a requirement which checks the activate to activate time of this runnable. How do we do that? First of all, we can view the start to start time of the runnable in a histogram. So we can see here on the x-axis again the time in millisecond, and here the number of instances that took 2 milliseconds, for example, from start to start within the trace that we measured. And here is exactly what we see. So on average, we have somehow start to start of 2 milliseconds, and we have some occasions where this happens in a higher frequency, and there are some outliers which are way above this 2 millisecond time frame. And here in these cases, we would definitely have some issues. So the problem that I showed you before here, so here we have around about 5.53, so it would be more than 5 or 6 milliseconds. So these cases definitely would be a problem if we violated this start-to-start requirement. So what do we do now? We define this as the zone where everything is okay. We have here more than nearly 7,000 instances that had the 2 milliseconds activate to activate. We have here a couple of activations around 3.5, where we have between 2 and 2.5 milliseconds. So we can monitor that with a lower severity level, and all the instances that take more than 2.5 milliseconds, this is something where we would have a violation that could cause the CAN communication to get dropped. So let's define requirements as shown here. How can we do that? In the TA tool suite, there is a requirements editor available, so you could search for the runnable that you want, in this case the CAN-TP main function. We want to apply the metric start to start. We want to define an upper limit with critical and major requirements violation. And if we do that, we can now define, okay, these different time zones. So we have greater 2 milliseconds, greater 2.4 milliseconds from start to start, would define these thresholds that I have shown here in yellow and red. And with that, we can now run it continuously against every build and get an indication if this error happened again. Good. So what tools do we need? Let's have a look at that. The solution that we provide for such timing issues is the TA tool suite, Timing Architects tool suite, which comes with 3 different options. So the TA tool suite is the base part of the tool, allowing you to import traces, to define requirements, define workflows, and all these things. And then depending on what you want to do with it, you have different options. The TA design allows you to define requirements, and it allows you to analyze in a graphical way the overall architecture of your system. So you can see which tasks you have in the system and which runnables are mapped to these tasks and how these tasks interact with each other. And this can also already be a very good indication if you think about splitting up different tasks to different cores, for example. You could very easily filter for the tasks that have no interaction with each other, for example. So to come up with ideas, okay, is it a good idea to split a task to a separate core, or maybe it's better to keep it because 2 tasks are closely connected. So much about the static view. On a dynamic perspective, we then have TA simulation and TA inspection. So what I have shown you before, this analysis of the task activations and the timeframes and the histogram, all these things are analyzed in TA simulation and TA inspection. So where's the difference? From a graphical user interface, there's no difference. Also, the features are basically the same in kind of how you analyze the timing. The main difference is TA inspection is working based on a recorded scheduling trace, and the TA simulation is working with a simulated scheduling. So how do we get there? First of all, The first input format that we have that is required for design and for simulation is a model in the TA tool suite. You can model from scratch. If you have a very complex AUTOSAR system, however, I would recommend you to better use the import. So you can use the ECU and system description and import it to the TA tool suite to get to a model. If you are using the DaVinci configurator, it's even easier. Then you don't need to search for the AUTOSAR files yourself, because you only need to tell the TA tool suite where to find the DPA file, so the DaVinci configurator project, and we will then know which files to import. This is enough for the static view in the design. If we want to get dynamic, we will somehow need to attach some runtime information to this model. So how long is a certain runnable taking to run? For that, you can use experience values. You can do budgets in the beginning of a project. You could also use the runtime measurement module in the microsar AMD, AUTOSAR monitoring and debugging cluster. This provides you with statistical values that you can then import into TA as well. On the other hand, if we are already on the hardware, we have the possibility to record a scheduling trace. So the state model that I showed you in the very beginning, basically you can use iSystem, Lauterbach, for example, or also the VX1000 from Vector in order to monitor the scheduling activities and write these log files. And the scheduling trace will then be imported into TA inspection so that you can analyze it against the predefined requirements that you have. And also very nice, from this trace, you're also able to update the timing information to the model. And of course, because we're talking about continuous integration, TA supports automation interfaces, and we have a workflow option or in the base part of the tool. So it's a workflow editor, which allows you to define your own workflows and replicate different interaction with the GUI of the tool so that you can run it in an automatized way and do the import and requirements definition and checking of requirements automatically. We will get to that in a second. So now that we know the tools that are necessary, which steps need to be taken in order to get to such a scheduling trace. Let's have an overview of the tool chain. So we have basically three different parts where we need to do something. The first one is in microsar. We need to configure the operating system. We need to configure the trace measurement hardware, record the trace, and then we will be able to import this into the TA tool suite and do the analysis. So how does it look in detail? Microsar. We will go to the DaVinci configurator, open our project, and under Runtime System General, you will find in the OS the debugging section. And depending on which trace measurement solution you are using, there are different headers provided for this hook setup. If you are using iSystem, Lauterbach, or VX1000, or you want to use them for this tracing, please send me a quick email. We have so-called timing bundles, which contain this header, scripts, and a step-by-step guideline throughout everything I'm showing you here very briefly. So these timing bundles contain a step-by-step guideline that help you to replicate this in your own project. Okay, so we have included the header now for the respective measurement solution that we want to use. So as a next step, we would then need to enable the VFB tracing. First of all, this can be found also in Runtime System Generals, RTE, VFB tracing, and additionally to enabling it, you will now need to activate the start and return hooks for every runnable that you're interested in. After that, you need to regenerate your DaVinci project and you will get a new OS awareness file. This OS awareness file needs then to be integrated by the respective timing measurement solution. So there's also in this timing bundle a dedicated guideline available step by step what to do in iSystem or Lauterbach in order to get this configuration done. I will not cover it here in today's webinar because it's part of the bundle, and there's also different webinars out there from iSystem or Lauterbach which show in more detail how the configuration is done. So let's consider the trace measurement solution is set up. As a next step, we would once more need to go back into the DaVinci configurator, and we will need to execute a script again. So we will execute the script to create the runnable measurement points. Regenerate the project, get a new binary, flash it to the ECU, and now we're able to record the scheduling trace. Once this is done, we can then very easily import this trace file into the TA tool suite. This now depends on the trace solution that you have. You will get different formats, but they all can be imported into TA. So, last chapter, how can it be automated? So we have seen all these steps that I showed you before, and in the first step, of course, that's some manual effort that you will need to do and that you need to spend for the project if you set it up initially. But however, once you have done that, this can be automated and you can easily reuse this within your build system. And for example, with every weekly or daily build, additionally, get some test reports about the timing behavior. How can we do that? What you can see here is one of the workflows that I mentioned earlier. So that's how a workflow in the TA tool suite looks like. Every of these green boxes is a job node, and each job node replicates an interaction with the GUI of the tool. So what this workflow is basically doing, it is loading your DaVinci project files and then importing the AutoSAR system description and ECUC to generate a timing model, which is then combined with a trace and evaluated, and a timing report is created. So these different steps and the input formats will be used by this workflow, and the workflow will with that automatically be able to combine all these informations and in the end provide you only with a timing report that you can then analyze. So much about that. I will now show you in a live demonstration how you can analyze the timing report with the TA tool suite and how you can work to come up with different ideas on how to solve an issue that you would find in a report. Before I switch to that, I want to offer you the possibility to reach out to me if you're having any specific questions that you want to discuss, project-specific topics. Can we set up such a toolchain in our project? Please feel free to reach out to me. I would also be happy to provide you with these timing bundles for the different trace measurement solution that I've shown in the presentation. You can find here my email. You can find a link to my LinkedIn account, and you can also scan the QR code to get in touch with me. Thanks for that. That's all for the presentation. We will now switch to the TA tool suite itself, and I will give you an overview on how to work with the tool itself. Okay, let's now have a look at the timing report that we can get out of the TA tool suite. First of all, something to mention here, this report is completely configurable, and you can adapt it to your needs. You can change the sort and everything. So I have here two different reports that I want to show you and explain you a little bit about. The first one is displaying the CPU load of different tasks. So you can see which task is consuming how much load on which core. Additionally to that, there's also a graphical visualization available. And this allows you to see, for example, how long or how much load different tasks cause within a certain core. So for example, here on the core 0, we can see that the task 1 millisecond is causing most of the load. So it's about 50% here. Additionally to that, what we can see is there are also some other tasks, like the 20 millisecond tasks, which show a lot of light green color here. So this means the task 20 millisecond is in 1.79% of the time. It's in the running state, so it's really actively running. But in 6.62% of the time, it's in a ready state. So it is preempted by another task, probably by the task 1 millisecond. So that's already an indication. Maybe we should have a look at that. There's some not very great scheduling activities happening. Here on the core 1, we have a similar picture. So you can see here that the task 2 millisecond is actually spending more time in this ready state, so it's more time preempted than it's really actively running. So the response time of the 2 millisecond task from activation to termination will in the end be quite long, when however the actual net execution time is lower. So that's one way to work with these reports. Additionally to that, you could also get a report out of that that looks like this. It simply lists all the requirements that you have, depending on the severity level for different metrics. So for example, what you see here, we have the task 1 millisecond, which had a response time requirement on 3 different thresholds for critical, major, and minor violations at 0.9, 0.8, and 0.75 milliseconds. So that's basically 90, 80, and 75% of the period. And this task 1 millisecond was running 2000 times in the measurement that we analyzed, and we can see how many cases were violated as a critical or warning requirement. So that's what you get for all the metrics and all the requirements that you have defined. So it's a very easy way to get a quick overview on how the overall timing behavior in the system is. So all the different timing requirements. And with the workflow that I showed you before, you would be able to get this very easily on a weekly, daily build basis, for example. So you could get this HTML report daily out to your project team, for example. They could check the report. If they see everything is green, no problem, then let's continue. But if you find some issues where you say, okay, I would like to investigate that in more detail, I would really like to find out what's the reason for a deadline being crossed, for example, then you can still go back to the TA tool suite and start the analysis in detail. And that's what we're going to do together right now. In the TA tool suite, we can now find the different options. So we have the base part, editing, design, simulation, and inspection. Simulation and inspection, I think I mentioned that before, are from the graphical user interface, from the functionality point of view, the same. The difference is only simulation is working on a simulated scheduling trace, inspection based on a recorded one. Okay, let's now assume we have received our report and we found some deadline violations that we want to investigate. How do we do that? The first thing that we see is here in this requirements table, we can again find the 1 millisecond task, which has here a response time requirement of 1 millisecond. So exactly at its period, it's a violation of the requirement. Now, what can we do with that? We can, of course, zoom out here a little bit. We can see here all the different tasks. So here's the task 1 millisecond, the one that we are looking at right now. And the deadline of the response time, basically what it does, it is checking for each activation until the termination if it takes more than 1 millisecond. So here, this will not be a violation. Here, we are also not violating the requirement. And here at this one, at the task 1 millisecond, here it looks like we have a problem. So here I would expect that the requirements would recognize it. So now let's take this requirement and drag and drop it into the Gantt chart. And what you see here now is that these red arrows popped up simply because of the reason here the deadline requirement of 1 millisecond was violated. And here actually this next activation again got a violation. And we can now zoom out a little bit again and scroll through, and by that find the different cases where my task 1 millisecond had a longer response time than 1 millisecond. If you want to visualize a little bit better what's happening at this point in time, for example, here where we have the start delay, you can see here that this was actually because this task input processing was still running. So only when this one finishes, our task 1 millisecond gets really active on the core. You can visualize that even better if you switch on this interference view here. And this now draws you red lines between all interferences between different tasks. So for example, for the next instance of the 1 millisecond task, we can see here that it's getting activated and it's running until this point in time. And here we now see that we have a preemption by an ISR. So every red line shows the interference in the scheduling behavior. Here again, here our task 1 millisecond interfered with the task input processing, leading to a start delay. Okay, but still that's not very systematic, let's say. Yeah, not very systematic. And one way to do that more systematically is the histogram. So we can not only use the histogram as we did earlier to define a requirement or think about good requirements, but it's also possible, of course, to visualize the deadlines now in the histogram itself. So we see again the response time of the task 1 millisecond and the number of occurrences. And we can see here the deadline requirement at 1 millisecond. So all the instances here to the left, they fulfill the requirement, they are green. And the other 139 cases can be found here on the right side of this threshold. So all of these requirements were violated by these instances. And we can now mark the most extreme outliers. So everything that's above 1.2 milliseconds, for example, we can mark them. We right click and we send this selection to the clipboard. We can now see here that there's a new line popping up in the clipboard. For the task 1 millisecond, and we find 16 instances in here. And what we can do now is we can double click them and we're jumping exactly to the point in time in the Gantt chart where the violation happened. If we combine this now with the interference view, it's very easily to see the reason for the violation of this response time requirement. So for example, here we see, okay, the task 1 millisecond had a very long start delay, which was caused by the task engine RR, leading it to be running very late and then violating the requirement. Let's go to the next instance and we see a very similar picture. So again, we have the task engine RR, which was causing a start delay, which then causes the task 1 millisecond to violate its deadline. And we go to the next instance. We see a very similar picture. And again, we can check some others. Yeah, again and again. So it looks like that all these requirements violations are caused by the long start delay, which is caused by the task engine RR. So with this kind of analysis and the knowledge, you can now start to think of solutions. So you could think about maybe introducing some offsets for the task activation so that they don't get activated at the same point in time and don't have so much start delays in there to improve the response time. Maybe the task 1 millisecond is more important than the other task, and we can change the priorities and just preempt the other task. This would be possibilities, or maybe it's also possible to split them up to different cores so that they don't interfere with each other. That would be something you would, of course, need to investigate in more detail. And here is actually exactly the point where it's very useful to have a simulation available additionally to the TA inspection. So if you have measured a scheduling trace and you found this kind of violation and you analyzed why is it there, and you come up now with 3, 4, 5 different ideas how to solve the problem. Of course, you can implement all these ideas. So you can introduce offsets, you can change priorities, and all these things. bring it down to the hardware, make a new measurement, and then again evaluate it in the TA tool suite with the recorded scheduling trace. But it's quite a huge step to do all these changes, get a new build, bring it down to the hardware, make a new trace recording, and then analyze it. So usually to get a new build done and test such an idea, I would say it takes at least a day to get this and be ready to verify it on the hardware. And if you then find out, okay, changing the offsets didn't help, yeah, it took one day. With the simulation, however, you can simply test such ideas very quickly. So you can change it, you can simulate, and you can then see if this looks like a promising solution that could help to solve the issue. And testing ideas like changing priorities, changing offsets, and so on, this is something you can do very, very fast in the simulation. So it would take you around about 15 minutes for each idea to test it. And then you can test 3, 4, 5, 6 different ideas within a couple of hours, and then just apply the most promising one on your hardware and then verify the result with the next build. I hope that provided you even a better overview on how to work with the requirements, how to analyze them, and how to come to conclusions in the end. If you have any questions, please feel free to contact me anytime. I hope you enjoyed the presentation, and yeah, thank you and goodbye.